Okay, so 3C is about the mean and the variance of the distributions that come to you in the form of a PDF or a CDF. This is nothing new. What's the mean and variance of a Poisson? What's the mean? No, it's lambda. Yeah? So if there's a 5 there in the brackets, the mean is 5. Okay, what's the variance of a Poisson? It's so simple, that's why I'm starting with it as well. It's 5. Okay, what's the mean of a binomial? N times P. And what's the variance? N times P times 1 minus P. If it's a normal, that's the mean, and that's the variance. And don't forget that the standard deviation is just the square root of the variance. Okay? So if you square out the variance, you obviously get back to sigma, and sigma is the classic Greek letter that refers to the standard deviation. Okay? Now, what about PDFs and CDFs? Okay? Well, you have to do some integration. So the mean of a continuous random variable is given by a integration procedure. You take the rule for the function, you stick a dx on the end, you go as far out to the right as you possibly can, which because of the general look of these things, you don't actually have to go out as far as you can, because remember how these things just suddenly conk out and become 0? That means for practical purposes that will never be an infinity, it will just be whatever your kick out point is. Okay? And this will never, for practical purposes, be a negative infinity. For practical purposes, it'll be whatever left endpoint your function just became 0. Okay? Now, the final thing you have to do is remember to put an x there. Okay, so you take the function, you multiply by x, and then do your core 2 thing. Okay? Now, the variance is given by a formula from Stats 1, which is the variance is equal to the expected value of the function squared minus the expected value of the ordinary function all squared. That's from Stats 1. Okay? Does everyone get the difference on that? If you're working out this fella, you just go like this. And then do your thing. Okay? Of course, remembering to put an x there. Whereas when you're doing this one, you do your thing, you put an x next to the fx, and you square all of that. Okay? Is everyone cool with that? Now, remember capital E x and mu are often interchangeable. In another part of Stats 2 we'll learn exactly when they're not interchangeable. But for practical purposes you should regard them as the same thing. Why does that make sense? Because the mean and what you would expect are the same thing if you just imagine the same experiment being done 1,000,000 times until the day you die. So I'll take you back to my flower pots example. 80% chance of them flowering, there's 10 pots. What are you expecting? Expecting 8. That's also what would happen if you did this every season until you died. Some years you get 10, some years you get 7, some freak years you get 3, some years you get 8, some years you get 8. If you average them out in the long run, you'll get 8. So that's why the mean and the expected value are two alternative expressions of the same thing. Okay, is everyone cool with that? Should we just bust down an example? Okay, so here's a PDF. It's got the classic look. So what's the expected value of that? So it's a PDF, it's got the classic look. What's the expected value? Just do your thing. Go as far to the right as you need, as far to the left as you need. Take your function, and for goodness sake, remember to multiply it by x. Okay, I hope you're not confused that I just wrote a y there instead of an x. Okay, because x is not the only letter. Okay, and then you do your thing. There's a bit of mathsmosis going on. So the answer is 4. So it's 4 times 8 2/3.
Did you integrate twice?
Why would I integrate twice? The integral of that is that, isn't it? If you differentiate that, you get that?
Yeah.
Why is your mathematics? Why have you put 4 out? The bracket isn't a quarter.
Oh, it should be a quarter, sorry. Thanks. So the answer is 2 1/6. Okay. Now what about the variance? The variance is, we've got to do that procedure again. We've still got to multiply by y, but this time we have to work on the square of the function we're given. But the fast part is we just take away, okay, and then you just mosey that through and you get the answer. Okay, is everyone cool with that? Now, a bit of Stats 1 revision. Do you remember these little pesky things? Do you remember how to handle those? Anyone remember?
To make a new table or...
It's supposed to be really quick. We've got an answer for EY. Our answer was 2 1/6. When you asked for E 2y minus 3, it's supposed to be super quick. You're supposed to take that answer and do something with it. What are you supposed to do? No, it's way simpler than that. You just times by 2 and take away 3. Yeah? In other words, you're using this formula. Yeah, it only works if it's linear. Okay? So double that, you get 4 1/3. Take away 3, you get 1 1/3. Okay? Now finally, what happens if you work out a variance of a linear function of something you've already worked out? Remember what to do with that? You times the previous answer by 4. Where does that come from? Does that ring a bell from Stats 1?
I remember times it by
The 3 is irrelevant. And why does this make sense? Because this is a measure of spread. If you have a whole bunch of figures, taking away 3 does not change how spread out they are. You know, if they're that spread out here, they'll still be that spread out when you take away 3 of them. But if you double them all, maybe they're like this, and then suddenly like this. Okay, so why do I times by 4? It's because the whole thing has been designed so that the standard deviation would get doubled. Okay, and therefore the variance would get times by 4. Does that make sense? You sure? Okay, so it's just a little bit of revision from Stats 1. Should we do another example? Yeah? Okay, so here's another PDF. It has the classic look. It's got a kick-in point. It's got a kick-out point. 0 otherwise. Now, in this actual text question from the book, it says to sketch that. What's the basic look of that fella? What shape is he?
Bucket down.
He's a bucket down, an upside down parabola. We know that as of 3 and as of -1, it's just 0. I don't really know a good way to do this other than to make it look really thick. Okay, now, if you put in 3 to this, what do you get? 3, oh, that's 0. Check it out. So it goes like that. If you put -1 in, what do you get? Well, that's 0 as well. Y-intercept is never hard to work out. The y-intercept is 9/32. I think. Am I right? Yeah? Okay, so there's the sketch. And remember the area under this fella is 1. Okay. So now they want the expected values, so we do an integration. If I do an integration of this, what will I get? Should be obvious. Am I home? If I just take this function and put it under an integral and just put the endpoints there, what do I get? You'll kick yourself in a second. Make sense? Why would that make sense? Because the whole point of a PDF is that it's supposed to express probabilities by working out areas under it. Okay? But that is not the expected value of x. The expected value of x requires you to put an extra x there as a product. Okay? So that's why we don't get 1. We get a genuine different answer. Okay? So let's work that through. Here's the mathsmosis. This is me getting the rest of it ready. So that's core 2 now. You mosey that through. You get you get 1. Now, why is that not a surprise? Why is it not a surprise that we just got an expected value of 1? Do not say because we got a 1 for this. You always get a 1 for that. There's something special about this example. What's super special about this example, which means that the expected value is 1? I'll give you a clue. It's like the normal distribution. What's the feature of the normal distribution? When I draw one of those little bell curves, it's symmetrical. Yeah, when something's symmetrical, like the binomial with a probability of half, that's a symmetrical distribution. The Poisson is totally not symmetrical. But this is symmetrical, so a little time-saving technique, the expected value will be 1, obviously, because it's the midpoint. Yeah? Of course you get that on average. Half the time you'd be over here, half the time you'd be over there. You cool? Sophie, you sure?
Yeah.
So it's a little time-saving technique for you. And finally, they want to know what's the probability that x is greater than 1. Now in the book, they've done that with a great big integration. They've just worked out the area to the right of that. But they're wasting their time. What's the area to the right of that, obviously? It's half, because it's half the diagram. Okay, so this whole thing I've just done there only works because the whole diagram is symmetrical. Okay, which just makes it no surprise that they've used a standard bucket. Okay, is everyone cool with that? Should we just do one final one, or are you good to go? Yeah, final one. This one is not symmetrical. Here's the classic. This is a pesky one that has 2 functions to it. 0 otherwise.
Yeah. Just doing that.
Yeah. So.
Okay, now I'm terrified I'm going to get this wrong, so I'm going to draw a little sketch. So it kicks in at 0. Kicks. Oh, wait on, that can't be right. I miscopied that. That's a 5. Kicks in at 0. First function kicks out at 3. The second function kicks in at 3. Second function kicks out at 5. Both straight lines. So one starts at 0 because if you put a 0 in there, you get 0. If you put a 3 in there, you get 6 over 15, which is 2/5, I think. Is that right? So that gets as high as 2/5. If you put a 3 in this, you get 2/5 as well, so it joins up. If you put a 5 in there, you get 0. So that's the graph. And that is obviously not symmetrical. Okay? Now the area under this had better be 1, is it? Half base times height. Half the base is 5 over 2, height is 2 over 5. 5 over 2 times 2 over 5 is certainly 1. So that's sweet. Now let's work out the expected value. The expected value, I'm glad you asked me to do this example because this is a crucial thing. How on earth are you going to do the integration when you've got two different rules? Well, you're in a tight spot, right? It's my job to tell you how to get out of the tight spot. The method is just do your integrations for their separate parts. So do your business for each of them. And for goodness sake, make sure that you're only integrating in the section for which that algebra applies. Is everyone cool with that? And then you just pump that through. Okay? Does anyone want to ask any questions about that?